Egunon, ongi etorri guztioi. Hi, welcome everybody. So let's start to be on time. There are some people that still are in the way with the public transport, but let's start now. And the first thing that I wanted to mention is a bit on the history of this event that is starting in 2016. When there were two groups doing quantum, or two main groups doing quantum here in the Basque Country. One was here at the university, was Queens, it's called at that time. Another that was in the APC, and was with Guess and some other people there. And we decided to do something or emulate something that was going on or happened in Austria at that time. They also have two big nodes. There's Innsbruck and Vienna, and they have regular meetings. And it's just to share what's going on in the community there in Austria, so we wanted to do something similar here in the Basque Country. And this is how it works and how we start. And well, after 8 years of all these things, the community has grown a lot. You have noted these things. Also, not only people here from the Egoalde, but also the people from France, from Bordeaux is joining this effort. And especially, there are, I think, also a strong support from institutions. Two main institutions has been created. One here at the university that is a global umbrella for all the activities in quantum, that is the Quantum Center, and the other is the BasQ Quantum. This is the big umbrella for all the activity that is going on around quantum in the Basque Country. So I think this is a nice move in how it's going the community. Something about the logistics and something about how it's going to be organized the event. So this is the campus. Here is where we are now in the faculty, the Science and Technology faculty, where it's happening the whole event. Here is the Paraninfo, where it's going to be all the talks in the morning and in the afternoon, and in the lunch break. And the posters will be in the grand salle. It's just going the corridor. Probably you have seen it all the way straight, and there will be there are panels there. In the first break, I invite the students or the people who are going to present the posters to please to hang the posters there and to show them. And then we will have also the lunch break there. This is the schedule that we have. It's a bit intense, so this is also nice. That there are plenty of activities now going on in the Basque Country. We will start with Iñigo now at 9:30, more or less, and ending around 6:30 with Tobias. And with this, I invite Iñigo to come to the stage. And Iñigo is a professor here at the University of the Basque Country. He has been working in quantum since his PhD. He did it here in the Basque Country, and he also was postdoc in the Walter Meissner with Peter Raber in Germany. And he's going to talk about the dynamical decoupling for cavity QED interactions.
Thanks, Enrique, for giving me the opportunity to talk here. Sorry. So, yeah, I will talk about dynamical decoupling of cavity QED interactions. Basically, cavity QED interactions, it's a synonym for the James-Cummings model. So, dynamical decoupling of the James-Cummings model. So, I will start introducing the James-Cummings model, which some of you may know. So the James-Cummings model describes the interaction of a two-level system with a single bosonic mode. It's in principle a paradigmatic model to describe the interaction between an atom and a single quanta of light, but it can also be used to describe in general interaction of different two-level systems with a single bosonic degree of freedom. So the Hamiltonian looks something like that. This term would represent the energy of the atom. This term would represent the energy of the electronic field, or sorry, of the electromagnetic field, and this would be the so-called James-Cummings interaction, right? The most distinctive feature of the James-Cummings model could be maybe the so-called Rabi oscillations of the James-Cummings model, in which the excited state probability of the atom, you can see oscillations of this excited state probability while the atom exchanges energy with the cavity field or the electromagnetic field. So while there is a coherent exchange of an excitation from the atom to the cavity. And this coherent exchange happens between the so-called James-Cummins doublet states. So if you start from the excited state of the atom, 0 photons in the cavity, you see exchange of populations between these two states, right? And depending on the total number of excitations you have, let's say in your system in the beginning, the rate of these oscillations sort of depends on the number of photons or the number of bosons you have initially in the system, right? So this James-Cummins model is behind many important applications in quantum technologies. For example, it's behind the preparation of non-classical bosonic states, such as, for example, in this experiment of trapped ions, where they prepared large Fock states in the vibrational states of these trapped ions in 2024. But it's also behind applications in quantum communications or in qubit photon interfaces, which are useful for quantum communications, for example. And also, if you want to explain how, for example, two spins that are embedded in a photonic crystal cavity like here, they talk to each other while being far away from each other, so they cannot see each other from direct dipole-dipole interactions, but they can see each other through the cavity field, right? So if you want also to explain, you want to model this system, James-Cummins model will serve for that, right? So traditionally, in the James-Cummins model, or in the context of the James-Cummins model, you would consider that the main decoherence mechanism leading the decoherence of the two-level system is the decay of the atomic excitation to other modes, which are not the single mode you are describing in the James-Cummins model, right? So this decay of the atomic state to some other modes or electromagnetic fields. But currently, there are systems in which the James-Cummins model describes the dynamics of these systems, in which the main decoherence mechanism is not the decay to other modes, but is dephasing, or more specifically, pure dephasing, which is characterized with this T2 star. So the main decoherence mechanism, or the main limitation, is not T1, which will be related with the decay, but it's T2 star. T2 star is then much smaller than T1. So it's then your main decoherence mechanism. And these examples of these systems are electronic spins in solid state, for example. Some superconducting qubits, such as flux qubits, also suffer from this. And also like rare earth dopants, other new technologies that are appearing, right, that also suffer from this characteristic that the pure dephasing time is much smaller than the T1 time. And since the times of NMR, we know that this pure dephasing time can be enhanced. Can be enhanced, can be improved if you are able to do something that's called dynamical decoupling, or a spin echo, right? And this T2 star enhancement, how does it work? So imagine you start with a spin under a magnetic field, so its precession frequency, or what we call the spin frequency, is defined by the value of a magnetic field. Then if you start in an initial state, in a superposition state, and you are in the appropriate rotating frame, so if you are in the rotating frame defined by this frequency, you should stay constant, you should stay indefinitely in this superposition state. But if your magnetic field has some fluctuations due to some noise you cannot control, what will happen in time is that this superposition state, you will pick up these two states will pick up a relative phase that depend on the value of the fluctuation that you don't know, right? After some time tau. Now, if you, at this time in the middle of the evolution, you make what's called a pi pulse, or if you invert the population of the excited and ground state, then you go from this state to this other state, and then in the second half of the evolution, the same state that picked up the phase, the G state, will pick up the same phase, given that if the fluctuation stays constant during this whole time, and then this phase becomes a global phase. And in quantum mechanics, we don't care about global phases So then what you will say is that you have had like a recovery of coherence, right? That's why it's called echo or spin echo. This recovery of the coherence, and then this process has been through decades applied to sort of maintain coherence in systems like NMR. Then, of course, if the noise is not constant during this time, or it slightly changes, you can always make pulses whose interpulse spacing is smaller and smaller, so that maybe the noise is not constant throughout this whole time, but is constant through this time, and then this gives rise to pulse sequences or dynamical decoupling pulse sequences, right? So the question we asked ourselves during this project was: is dynamical decoupling compatible with the James-Cummins model? So imagine I have my two-level system. It's interacting with a bosonic mode. I want to protect this process. Is it compatible? And in principle, the answer is not trivial, because the James-Cummins model involves dynamics between these two states, within the James-Cummins doublet. So E0 and G1 would be the states involved in the James-Cummins dynamics, while the pi pulse, which is the feature in dynamical decoupling, involves exchanging population between these two states. So the pi pulses take you away from the subspace of the James-Cummins model, right? And that's why, in principle, it doesn't look like if you want to try to protect a transfer of a two-level system excitation to the bosonic field, then you will get spoiled if you make a pi pulse, because you will get out of the subspace, right? So the spoiler, the answer is yes, it's compatible, right? And if you want to take a message from this talk, this should be the message. It is compatible, and what we did in this work is to prove that if you are able to do if you are able to interrupt the evolution of the James-Cummins model with fast pi pulses, then from something that in the beginning would look like that because of the dephasing noise you are suffering, so something that would look like an imperfect Rabi oscillations, due to dephasing, you can in principle make it, you can in principle recover the full dynamics of the James-Cummins model using this dynamical decoupling. So now it will get a bit more mathematical, unfortunately, the talk. So I will try to explain you how we did this, or how we found out that this is possible, right? Actually, I will try to talk about two, how you can protect two processes. One would be protecting the James-Cummins interaction, and another thing would be how you can protect cavity-mediated interactions that are also described by this James-Cummins model, and then I would conclude my talk. So I will start with my James-Cummins model, and then my driving Hamiltonian. So this driving Hamiltonian would describe the pi pulses, right? I am also going to assume that I am able to rotate my qubit along the x-axis or the y-axis, right? And this here is the James-Cummins Hamiltonian, where this delta basically tells me how was the detuning between my cavity and the two-level system, and this psi term represents the noise, the unknown noise that I have due to these fluctuations of the magnetic field or whatever. No? So how we do it is we move now to the so-called toggling frame. So it's a frame that sort of puts you in the goes along with the drive with the pulses you are doing. So if you go to this toggling frame, what happens is that the Pauli operators now flip their sign depending on the pulses you have done. So if you do a x pulse or a pi pulse along the x-axis, that will be like represented here in red, then the sign of the Pauli matrix Y and Z flips. And if you do a Y pulse, then the sign of the X and Z matrices flip, right? So that's basically how it looks like now in the toggling frame. So if you will write down the Hamiltonian in this toggling frame, this interaction picture is the same thing. Now, what one can ask, what's the dynamics going to be like after one period? After one period of my sequence, one period of my sequence will be something like that after 4 pulses, right? So after here at the end, how my dynamics will look like, and turns out that if the pulse sequence period is small compared to the relevant constants here in my Hamiltonian, the dynamics is well described by an effective Hamiltonian. So the dynamics will behave as if the governing Hamiltonian is actually this average or effective Hamiltonian, which is given by an integral of this Hamiltonian over here. And the integral of this Hamiltonian, what it involves is they are integrals of these f functions, right? So if the integral of my f set function over a period is equal to 0, it means that this term here will not have an effect after a period. This term here was the term that represented the noise. So this means that after a period, noise will have no effect in my dynamics. So I would have protected my dynamics. Here, however, if the fx and fy integrals are also 0 after a period, it would also mean that the James-Cummins interaction disappears effectively after a period, right? So what we need is to come up with a pulse sequence that after a period obtains 0 for this integral, but not 0 for these two integrals, right? So if you try, for example, with the familiar xy sequence, what you will end up getting is that, for example, if you consider the integral of this fz function, you can see with your eyes that the integral will be 0, right? Because half of the times is up, half of the times is down. So the integral will give 0. But unfortunately, the same happens for the fx and fy functions too. This means that after a period, effectively, your system will not have evolved because you will have cancelled out effectively the noise term and the interaction term, right? So if now we try with another sequence, which is xxyy, then something different happens. Now the noise will get cancelled too, right? This f set integral will be 0, but the integrals of fx and fy will not be 0, will be 0.5 or so. So what you will end up having is what you wanted. So you will end up having, after a period, that the effect of the noise is equal to 0, but you will have an you will still have the effect of the James-Cummins interaction with the caveat of having your original coupling over 2, so with half of the original coupling, right? But you still are able to recover the James-Cummins interaction. It's also, I wanted to mention that if you consider rotations only along one axis, you are not able to recover the James-Cummins interaction. So if you consider, for example, the more simple XX, 2 pulses, then you will end up having an effective interaction that looks something like that, which is an interaction that resembles to what we call the Rabi model or the quantum Rabi model, right? So what we did is we considered different pulse sequences, and also we considered different values for the detuning between the cavity and the two-level system, and we here classified what's the interactions you get depending on the sequence and the tuning, right? And we ended up noticing that one can not only recover the original James-Cummins interaction in your system, but also somehow engineer different interactions, such as the anti-James-Cummins, for example, that will be this other one, or these Rabi models these Rabi interactions that I was just talking about. No? So you can, in principle, not only recover the James-Cummins interaction, but engineer different interactions. And you can also decouple the system completely, let's say, from the interaction term. And this table here is meant to represent that. Okay. So here now we tested then how well this works. So for that, we considered something we want to do with our James Cummings model. So we want to do a state transfer. We want to start from an excited state in the two-level system and 0 in the cavity, and we want to exchange this excitation to the cavity. And if we consider now the fidelity of this process versus the strength of the noise, of the pure dephasing noise, which would be represented here by sigma, like inversely proportional to the pure dephasing time, you see that without pulses, then the fidelity decays here with the gray line. But if we are able to introduce 64 pulses, for example, depending on how you do it, with which sequences, here we consider 2 different sequences. Now you see that the fidelity decays, but much later than for the pulse-free case. So it can maintain high fidelities for higher noise strengths. Now, if we want to, now we looked into how this scales, let's say. So how it scales with the number of pulses. So the error that is given by the error that is produced by the dephasing over the number of pulses, we see that it decays, and we see that the error decays with the 1 over the square of the number of pulses. Since the error of this process depends on the square of the noise strength, one can interpret that the dynamical decoupling, what it does is effectively it decreases your noise strength by a factor equal to the number of pulses you're introducing in the system, right? Yeah, this is a noise. This is a figure also proving that we can generate dynamics that are not James Cummings dynamics, but dynamics given by this quantum Rabi model, right? So then we considered this other case, which is the entanglement generation of cavity-mediated interactions, right? Imagine we have now two-level systems that are not talking to each other directly, but through a cavity field, right? So the Hamiltonian you would write down would be this, which is called sometimes Tavis-Cummings Hamiltonian, but it's the sum of James Cummings Hamiltonians. And if it happens that now if these two-level systems are far detuned from the cavity frequency, so here the cavity, for example, could be a mode of vibration of or in this nanomechanical structure, right? So here, what I have in mind with this picture is 2 spins, they talk to each other through the vibrations of this lattice, of this mechanical oscillator, right? So if you are now in a regime in which the two-level systems are far detuned from the cavity, then you can write down an effective Hamiltonian instead of this one over here. You can write down an effective Hamiltonian, and you end up obtaining that the spins will talk to each other through a flip-flop type interaction with an effective coupling of that equals G1, G2, with G1 being how strongly the first spin couples to the cavity, G2 how strongly the second one couples to the cavity, and the delta would be the detuning. Now we ask ourselves, is the dynamical decoupling compatible with this process? So imagine we want to, for example, we want to start from a product state, and we want to get a perfectly maximal entangled state. This can be done with this Hamiltonian, with this flip-flop interaction. Now, what happens is that the pi pulse will take you, if you do the pi pulses on both two-level systems at the same time, will only take you from this state to this other state. So it's the same subspace that is involved during these pi pulses and during the flip-flop process. So that's why the dynamical decoupling is sort of trivially compatible with this flip-flop interaction. How one would see it from this toggling frame perspective is that under the toggling frame transformation, this flip-flop interaction is invariant, let's say. And then the Hamiltonian in the toggling frame will look something like that. You would have the noise term multiplied by this fz function, but this flip-flop interaction would remain will remain constant. And then if your pulse sequence is, the period of your pulse sequence is small compared to the relevant coupling constants, then you would be able to cancel the effect of the noise while still maintaining the flip-flop interaction. In this case, not even with a reduction in the coupling constant, just with the original coupling constant. All right. So then what happens is, well, then if it's compatible, then what we did is we compared, we took a figure of merit. So how we want to do entanglement generation with this flip-flop interaction. We start from EG, we go to this state, and then we measure the fidelity, how well we are able to produce this state under noise, right? So for 0 pulses, we see that the fidelity starts decaying at this point with the gray line, right? With noise strength. Then we start introducing pulses, and we see that the pulses help with the fidelity. So we are able to maintain fidelity for high fidelity for higher noises, for more pulses. But eventually, we end up having something weird. So if we introduce 1,000 pulses, for example, we are not able to get good fidelities anymore, not even for small noises. So there is something goes wrong for the 1,000 pulses. And what goes wrong is that the tuning, which was the largest frequency in the game, is not longer the largest frequency whenever you introduce too many pulses, right? So for 1,000 pulses, what happens is that delta times the period of your pulse sequence is similar to 1. So then this dispersive regime and the assumptions we have done before require now both that the tuning have to be bigger than G, but also than this 1 over the period, right? So basically, what we had to do is go to the original Hamiltonian, then go and do the things properly, no? To derive the second, the first and second order Hamiltonians, etc. And we end up discovering that we are able now to, well, the dynamics will be now described by the sum of 2 Hamiltonians. This will be the first order Hamiltonian, something very similar to the Jeans-Cummins with two spins, and a second order Hamiltonian. And playing with these two, and playing with the detuning and the pulse sequence, what we end up having is that we can generate effectively, we can engineer icing interactions which were not present in the original model, which only had flip-flop interactions. Flip-flop interactions can also be done. Flip-flip interactions can also be done. So in this figure, I'm trying to demonstrate this. So, for example, in the icing interaction, if you start with the EG state or GG state, in any case, you will end up in a Bell state. So here I'm plotting in red the concurrence. So concurrence will go to 1 at some point, and so on. And with the flip-flop and flip-flip, a different thing happens. Right, so I think I will move a bit now to the conclusions of this section. So what we did is we wanted to see now what's the gain in doing these pulses in this cavity-mediated entanglement generation, and turns out that the error of this process is usually, I want you to focus on this thing here. The error is usually limited by a dimensional quantity called the cooperativity. And cooperativity in this context is it would be G squared over sigma times kappa, where sigma and kappa are the noise processes that are going on here. Sigma would be the noise process of the two-level system. Kappa would be the noise that the cavity field is suffering. So the conclusion was that the introducing these pulses is like enhancing your cooperativity with a factor that is equal to the number of pulses. That's a bit the conclusion of this second part. And with this, then I would like to finish my talk. So I talked to you about a protocol to protect these cavity QED interactions with dynamical decoupling. So we not only are able to suppress the effect of the noise, but these pulse sequences are also able to engineer interactions that were not present in the original system. And the gain given by these pulse sequences can be easily interpreted in the case of the James-Cummings model, by let's say, dividing the noise by effectively dividing the strength of the noise by the factor equal to the number of pulses, and in the case of cavity-mediated interactions, multiplying your cooperativity. Now you will have a new effective cooperativity, which will be the old cooperativity times the number of pulses. So with this, thank you for the attention.
Thanks, Iñigo. Comments or questions?
Okay, thank you, Iñigo, for the very nice talk. I was just curious about in the slide that you show that for 1,000 pulses, the decoupling is no longer the dominant frequency. Yeah, I was just wondering why you have chosen to put 1,000 pulses. I mean, it's like when you start increasing, it starts improving, and suddenly in 1,000 pulses, it goes all wrong? Or is just that for a high number, it goes wrong, and you have chosen 1,000 as a representative number?
I chose it as a representative. So it's not that at 1,000 something weird happened, but at very high, when these conditions start to fail, let's say, then something else happens. Right?
Okay, thank you very much.
Thanks.
Hi, Iñigo. Thanks for the talk. So I have two questions regarding more the cavity itself. So the first one, pretty naive. So doesn't the cavity mode have decoherence itself too?
It does. And this has to, you have to take this into account. Let's say. This we took it into account I went through it very quickly, unfortunately. So if you, for example, want to entangle two spins that talk to each other through a cavity, and then the cavity also transfer its excitations through processes that you don't know to other modes in the system, this could be represented by this kappa. And this would be like sort of the decay time of the cavity. And this kappa is relevant, and it will limit the fidelity of this entanglement you can generate. And yeah, that would be a bit the answer.
Yeah, okay. And then
now, yeah, sorry, yeah, tell me.
So the cavity modes are always bosonic modes, as far as I understand, but they can be, as you said, vibrational modes or photonic modes, I guess. Yeah. So especially if they are photonic modes, don't they interact with the radiation that you send usually to the pi pulses or the control drives?
Depends on the. Yeah, I mean, in principle, you would. That's. So if you have I mean, I would say that you are maybe a way you could drive this two-level system would be through the cavity mode. So you sort of send light to the cavity, and this light could be a pulse, a laser pulse, and this would enter into the cavity and would effectively generate a rotation of the two-level system. So does interact with the radiation? Yes, it can interact. I mean, it can directly interact in general, but you could also have other mechanisms in which sort of you are able maybe to rotate the state of the two-level system without affecting the cavity field. But yeah, in general, you should, in principle, take this into account too.
Okay, thanks.
Hi, I have a related question to his question. So this process relies heavily on how well you can perform the pulses, right? Mm-hmm. Does this kappa also account for imperfections in those pulses?
The kappa?
Yeah.
These ones? This one, but why would this kappa would be related with pulse imperfections?
I'm asking if that's the case.
In principle, I mean, pulses, you can, definitely pulses can have imperfections because, for example, let's say, you don't know often what's the field amplitude that the two-level system is feeling of your external field, right? So this will lead to imperfect pi pulses, etc. And then there are sequences that are robust somehow against these imperfections. So this we do take into account. Let's say we use pulse sequences that are known to be robust against imperfections or in these external fields you are introducing. In terms of how kappa would be affected by these pulses, it could also be that, you know, what happens is, I think often in experiments is you introduce radiation in the system, and then this also could affect, as Paul said, that the bosonic field, and could even maybe make the coherence of the bosonic mode bigger, maybe because we are heating the sample or something like that. So this could also happen, but we did not consider this in the model.
Okay, we have to move, so we thank again Iñigo, and we go to the second speaker.